When we talk about distances, we're usually talking about going from point A to point B, and that's a straight line. And when we talk about distances, we're usually looking for what is the length of that line. Occasionally, we might be interested in, depending on the scenario, what the distance is based on not a straight line, or even a curve. Well, that's work for calculus, so we won't be doing anything like this in this class. We're not quite ready for that yet. We know how to do these, and we know how to find the distance between these 2 points by taking the shorter distance between the points between those two. For example, I could go from C to this point and then that one to that one and measure those shorter distance and just add them all up. In trigonometry, though, we're going to be looking for the distance between two line segments or two rays. So let's do a little bit of vocabulary review. This is a point, and actually it's not. It's far too big to be a point. A point is infinitesimally small. If you take a bunch of points and line them all up, this would literally take me forever. So I'm not going to do that. And in fact, notice that I'm missing some points in between 2 points, right? There's another point in here, and another one in here, and another one in between those two, and so on. But if I take a whole bunch of these points and just stretch, line them up and stretch them out, I can do that forever, and I get what we would call a line. Now, a line goes on in both directions forever. So when we're talking about a line, and we actually mean a line, we need to include arrows to indicate that. If you just want part of a line, we have a line segment. And usually we indicate the ends of that line segment with 2 points. But what about having a line that ends on one side in the same way that a line segment would do, but keeps going in the other direction forever? That's called a ray. And if you join 2 rays at the same endpoint, this is what we call an angle. Now we have to be careful here because there are actually 2 angles here. One that goes from this ray to that ray, and one that goes from this ray to that ray in the other direction. So there's a large angle, this one here, and a smaller angle. We'll get into that just a little bit more in a few minutes. The thing is, when I want to measure the distance between these 2 rays, this angle, I can't just measure the distance along a straight line. I'm measuring sort of part of a curve. Notice if I come way out here and start measuring, I'm not quite going to have room to do this on the other side. My circle won't be quite big enough. Okay, that I get the yellow part of the circle and the pink part of the circle, or I get the smaller yellow part of the yellow part of the smaller circle and the pink part of the smaller circle. But the ratio of yellow to pink is the same in both cases. This looks like maybe 25% of my circle, and this is the other 75%. I've not done a good job of drawing the circle here, but here's about 25% of the circle, and here's 75%. So it doesn't matter how big the circle is, you end up with the same proportion of circle if you're measuring the inside angle versus the outside angle, regardless of how far away from the common point you start, right? So we have to find a way to measure the distance in the rotational distance between these 2 rays so that the answer that we get is the same whether we're measuring this curve here or this curve here. Now this one is shorter. This curved arrow is shorter than this curved arrow. So if we were measuring what we call the linear distance, the distance along this curve, we would get one answer. While if we measure the distance along this curve, the linear distance along this curve, we get a different answer. So that's not going to help us decide what the rotational distance is between these 2 rays. We need to find a a way to measure that distance in a rotational sense so that the answer is the same regardless of which of these 2 points we're starting at. And the thing that we use to make that measurement is called a degree. That's the unit that we use to measure angles. Okay, this number of degrees is the same as this number of the degrees. It's how many rotations you have to make to get from this ray to this ray. Imagine standing at the middle of this thing and facing out in this direction, and then not moving from this spot, turning your body so that you were facing in this direction. Well, no matter whether you're staring at this point or staring at this point, your body is going to have to turn the same amount in order to get to the place where you're looking at either of these points. Your face is pointing in the direction of either of these 2 points. So that amount that you turn is measured in degrees. Or at least that's what we learned in school. There's another unit that we can use, and that's called radians. So we can use either degrees or radians to measure rotational distance, to measure angles. Degrees are pretty small. If you think about a circle, in other words, if you think about starting facing in this direction and turning your body so that you're facing in this direction and then in this direction, and you go all the way around, we know from high school or maybe before that there are 360 degrees in a circle. As we'll learn in a minute, there are about 6.28 radians in a full circle. Well, that's kind of a weird number, but there's a reason for it, and we'll come back to that in a few minutes. Before we go on, I want to point out one other thing here, vocabulary-wise, that wherever we start our rotations, we call that the initial side of the angle. And wherever we end, we call that the terminal side of the angle. Notice in this diagram that I have here, if this is my initial side and this is my terminal side, I can still either start here and end here by going along this short yellow arrow, or I can start here and end at the same place by going along the outside, along the pink curved arrow. So which is the initial side and which is the terminal side is not affected by which way I go. But if I start here and go in the other direction, then I'm going in the opposite direction. So as we'll learn at some point a little bit later down the road, we would consider this a negative angle measurement, whereas this is considered a positive angle measurement. So which is the initial side and which is the terminal side does matter, even though we can't use this information to tell whether we're going the short way around from the initial side to the terminal side or the long way around. All right, let's take a look now at where this 6.28 comes from. How many degrees are there in a circle? 360. How many radians are there in a circle? 6.28. Well, that's actually 2 pi. But let's talk about why that's the case. Here are 2 circles, one inside the other. And if I find the center and I take the radius of one and the radius of, let me use a different color, the radius of the other, the radius of the small one is white, the radius of the large one is yellow. Maybe I should use a slightly heavier pen here. There's my smaller radius. Then what I want is to figure out what the relationship is between the radius of the circle and its circumference. Well, regardless of the measurement of the radius, that one's going to be, I'm going to call that one little r, and I'm going to call this one big R. we know that the circumference of a circle is 2 pi times its radius, 2 pi r. What's the relationship, or what's the ratio between the circumference and the radius? If we divide both sides by r, we get 2 pi. And so this tells me that the circumference of any circle divided by its radius will always be 2 pi. Another way to think about this is you take the circumference of a circle. Let me grab another pen. I'll use a different color again. If you take any circle and you divide it up along its arc into chunks that are the same length as its radius, you'll get, that's 3, 4, 5, 6, and a bit, or about 6.28. And that's 2 pi. 2 pi is about 6.28. It's actually, let's see, 6.28318553, and so on. Now, if I replace this little r with a big R, I'll get the same relationship. So it doesn't matter what the size of the circle is, doesn't matter what its radius is, the relationship between its circumference and its radius, or the ratio, is always 2 pi. If you take the circumference of a circle and divide it up by radius lengths, you'll always get 2 pi of those lengths. So we call one of those lengths a radius, or, because we're kind of trying to distinguish it from radius, we call it 1 radian. Now, we haven't talked about this yet either, and we'll get to it in a few minutes, but there are a couple of things that we consider standard. One is that when we use a circle to measure either radians or degrees, it's conventional to start at this position here. If I were to superimpose a set of axes here, there's my x-axis, and there's my y-axis, then my circle is centered at the origin. And the first position, or if I say 0 degrees or 0 radians, what I mean is starting with the initial side of the angle, or the initial ray, lying along the positive x-axis. It's also conventional or standard to think about traveling in the counterclockwise direction. So I'm going to go in this direction. Now, if I do that, start here and go in this direction, then if I go all the way around the circle, because imagine I'm standing here and just turning my body so that I'm looking at this point and then looking at this point and then looking at this point and so on, I will have turned my body 360 degrees, or 2 pi radians. If I only get halfway, I will have gone 180 degrees, or half of 2 pi radians, which is pi radians. All right, I've run out of room, so I'm going to go to the next screen, and we're going to talk a little bit more about some common angle measurements in both radians and degrees. We've already talked about the fact that if I start in the center, facing along the positive x-axis, and I turn in the counterclockwise direction, my starting point is what I'm going to call 0 degrees. I haven't turned at all. Well, it's also 0 radians because I haven't turned at all. If I go all the way around the circle, I've turned 360 degrees, or 2 pi radians. Halfway around the circle is 180 degrees. Half of 2 pi is pi. If I stop here, I've turned 90 degrees. That's half of a circle. Well, that's half of pi, or pi over 2, which is how it's commonly written. Half of that is 45 degrees. Well, that's half of pi over 2, or pi over 4. And so on. Halfway between 90 and 180 is, there's 180. Halfway between 90 and 180 is here. And that's going to be 90 plus 45, or 135 degrees. And if I think about this in terms of how many pi over 4s there are, there's 0 pi over 4s, there's that one, 1 pi over 4, 2 pi over 4s, 2 times pi over 4 is pi over 2, 1, 2, and there's 3 pi over 4s, so 3 pi over 4. And I can do the same thing down here. Halfway between 180 and 360 is 270. And let's see, I'll put that in here. Now I might want to be thinking about how many pi over 2's. Here's 0 pi over 2's. Here's 1 pi over 2. Here's 2 pi over 2's, which is pi. Here's 3 pi over 2's. So 3 pi over 2. Halfway between 180 and 270 is 225, so 225 degrees. And halfway between 270 and 360 is 315, so 315 degrees. So 225 is here, and 315 is here. So now I'm going, if you look at the size of this angle here, use a different color. This angle here, what we decided was 45 degrees, or pi over 4. That's the sort of unit that I'm using to measure these, right? That's 1 pi over 4. That's 2 pi over 4's. 2 pi over 4 is 1 pi over 2, or pi over 2. Then I have 1, 2, 3 pi over 4. 4 pi over 4's is pi. This one's 5 pi over 4. Then I have 6 pi over 4, which if you reduce it is 3 pi over 2, and then 7 pi over 4. I have 7 pi over 4's. 1, 2, 3, 4, 5, 6, 7 pi over 4's. Add one more and you get 8 pi over 4's. Well, 8 over 4 is 2, so that's 2 pi. So I've gone all the way around from 0 to 2 pi in radians, measuring with an angle no smaller than 45 degrees, or pi over 4. So these two angles are equivalent, right? These two angles are equivalent. If I ask you to convert 225 degrees into radians, you can just say, well, it's 5 pi over 4. What if I ask you to convert 220 degrees, or 273 degrees? We'll come to that in a minute. There is a way to do that. Before we do, though, I want to point out that the common angle measurements that we often use in trigonometry for exact values include not only measures of multiples of 45, but also measures of multiples of 30 and 60. So I'm going to insert in here 30 degrees, and in here 60 degrees. And I would do the same thing then here, and here, and here, and so on. I can use the same argument, or the same logic, to say that a 30-degree angle, which would be about here, is a third of a 90-degree angle. So I would have 1, 2, 3 of those in this 90-degree angle space, right? There's a third, 30 degrees is a third of 90. Well, since 90 is pi over 2, a third of that is 30, a third of this is pi over 6. So another way to write 30 degrees is pi over 6. And a 60-degree angle is really just two 30-degree angles. Let me highlight that one so you can see what I'm talking about here. Let's use green. This is a 60-degree angle. But it's made up of two 30-degree angles. There's the first 30-degree angle, and there's the second 30-degree angle. So I can either think of this as 2/3 of 90, or twice 30. 2 times 30 is 60. 2 times pi over 6 is pi over 3. And then I can count my way around the circle using the same logic. How many pi over 6's do I have? How many pi over 3's do I have? All the way around. We're going to come back to this chart, if you will. So I'm not going to bother to do that now. But you can go figure that out and decide what all of these values should be and what all the in-between values should be in terms of radians. The thing to remember at the moment is that radians are radiuses, and that there are 2 pi radiuses, or about 6.28 radiuses, as you travel around the circle. And that's where that term comes from. A radian is a radius, and that's why there are 2 pi radians on any circle. Now, I imagine you might be a little bit confused at the moment because I've been saying right from the very beginning that I'm going to teach you trigonometry using the right triangle approach and not the unit circle approach, at least not at first. This is the unit circle. So if you were wondering what the unit circle was, well, that's what it is. But if you've seen it before, then you already know what this thing that I'm building here looks like and probably how to use it to a certain extent. But I'm not going to use it to describe what sine and cosine and tangent are. I'm going to use a different approach for that. But when I do, I'll be talking about my angles in both radians and degrees. So we need somewhere to start. We need a place to start talking about radians, which for many of you at least is a new or unfamiliar unit of measure. Now, remember a minute ago, I asked you, what if I asked you to convert, say, what did I come up with? 273 degrees. How many radians is that? Well, let's take a look at one particular measurement that we took here. We talked about going halfway around the circle, and that we said that that was either 180 degrees or pi radians. Those two things are equal. So I can say that 180 degrees is equal to pi radians, and then I could divide both sides by pi. And I'd get 180 degrees divided by pi radians is equal to 1. Equally, I could divide both sides by 180 degrees. And I'd get that 1 is equal to pi over 180 degrees. In other words, the ratio between these two things, no matter which one's on top, is 1. So if I take any angle measure and multiply it by either of those ratios, I'm really just multiplying it by 1. It's a kind of dimensional analysis. If you've taken any chemistry, you'll know what I mean by that. You're taking something measured in 1 unit, degrees, and multiplying it by a very specially designed version, if you will, of the number 1. Multiplying anything by 1 gives you the same value back, but in a different form. So what I can do now here is cross out or cancel my degrees, and I have 273 pi over 180 radians. This was in radians. That simplifies to 91 pi over 60 radians. So 273 degrees is equal to 91 pi over 60 radians. Simple. If I give you an angle in radians, for example, 2 pi over 7, and I ask you to convert it to degrees, first of all, I can recognize that it's in radians because it has a pi in it. So now it's in radians. I want to multiply it by 1. This time I'm going to multiply it by 180 degrees over pi. And when I do that multiplication, the pi's cancel, and I get 360 divided by 7 degrees. That doesn't reduce. So that's my answer. This is how many, oops, wrong pen. This is how many degrees 2 pi over 7 radians is. So I used the fact that these two were equal, 180 degrees is equal to pi radians, to build this formula, if you will. I have either this version or this version, depending on whether I'm converting from degrees to radians or radians to degrees. If I have degrees in my problem, this is like saying 273 over 1. If I have degrees in my problem, I'm going to want to cancel the degrees. So I'm going to want to use the over 180 version to cancel the degrees. If I have pi, if I have radians in my problem, if I have a pi in my problem, I'm going to want to cancel the pi's. So I'm going to use the 180 over pi version. I could also, for those of you who are astute, you might have noticed, I could have taken the whole thing and said that 360 is equal to 2 pi. 360 degrees is equal to 2 pi. Well, if I divide both sides of that by 2 pi, I still get 1 here, but here I can reduce. 360 divided by 2 is 180. So I still get 180 over pi equals 1. And the same thing happens if you use 2 pi over 360. So that's why I use the 180 and the pi and not the 360 and the 2 pi. It's just a little bit less messy. Remembering this ratio means that you don't have to memorize these formulas, but they're pretty easy to memorize anyway. You just have to remember which one to use depending on which conversion. Are you going from degrees to radians or radians to degrees? So in this video, we've talked about what an angle really is and two different ways to measure it. In the next video, we're going to talk about what it means to be in standard position.